Hello students, we are going to start a new chapter, okay, and this is lecture number 15 and we will start a new chapter, chapter 4. Okay, so far what we have learned is, given a problem, for example for a structure problem, yeah, we have some differential equation. Okay, so for example for this we had d over dx ea du over dx plus b equal to 0. This is for a structural analysis problem or the stress analysis problem. Similarly, we have derived it for different problems like heat transfer problem and diffusion problem. Yeah. Now, we have tried to solve also using two methods. Yeah. One we use the Galerkin method, and the other we used Rhys method. Right. Okay. So the starting point for both of these methods were different, right? So Rhys method was more of related to the potential, the minimization of potential energy based on that. So we had different kind of formulation for that. For Galerkin, what we did, this is a strong form, right? A strong form, and from there we change to the weak form. Yeah, and then we do the, when you assume some approximate solution, right, we assume that ux, and there is a weight function as well, right, that we assume. So weight function that is wx, and based on we derive. So we will be in this course, we will be mostly working on the Galerkin method only. Okay, Rhys method, just to tell you that there is another method that exists, and but here we will start from the differential equation, and this differential equation we are going to the first convert into the weak form, and then we are going to solve it. Our method is clear, our method is Galerkin method only. Okay. So once we have that, next thing is that what kind of ux we can take, yeah, and how the finite element method is different. When you say finite element method, so we will be using the Galerkin method only, but main difference is the choice of ux, how we are choosing ux and wx. So this is, so far what we did was we had some test function you used ux, for example we can take as alpha naught plus alpha 1x, kind of this one, right. In finite what you see here is basically for the whole domain, right, for a whole domain from here to here we have a single solution and goes like this one, right, and then the actual solution, which could be something like this one, what you get is your solution is you are getting like this one. Well, what we want is, we want to have this kind of linear solution only, but we want such a way that still it is accurate. Accurate means closer to the actual form. So we want this kind of solution rather. Yeah. So basically the finite element method really means is the finite element method basically introduces the concept of elements. Right. Okay. So it introduces some elements, meaning that the solution we are offering will be ux will be piecewise polynomial. Okay. So instead of having the solution in like something like this, where this will be something, solution is something like this, right? You are assuming this solution, which is this is equal to ux, this is ux, is equal to alpha naught plus alpha 1x. So from here to here will be alpha naught, right? And the slope will be alpha 1, right? The slope is alpha 1. Okay, the slope is like this. So instead of using this kind of thing, we are going to use something else. So we want solution to be something like this, you know. So we should be able to find, like from here to here one, from here to here the other one, yeah, from here to other, like this one. So this one is piecewise polynomial. Okay, so what is the meaning of that? This meaning is that we can have a like you have a domain like this one, and then you will say you are going to let us say have two linear elements. Element meaning that you will have a node here. So the see here, this is a node. So that you have, this is a node here, this is a node here, this is a node here, right? Okay, you know the concept of node already. It's a node number 1, node number 2, node number 3. Yeah? And then you are saying that within these two nodes, your solution may be the linear. So it could be from here to here, could be u like this, from here to here u will be like this, right? So you can say this is u1x, this is u2x, where 1 meaning this is this one is element number 1, this is element number 2, means within element number 1 the displacement will vary like this, within element number 2 this will vary like this one. So that you do not have the common u to represent the displacement in both the elements. So instead of having one displacement going like this one, you can have two displacements functions, right? And that may, if the actual solution is a curve like this one, these two combination, the combination of these two linear displacements is more close to this quadratic solution rather than having just one like this to this. So this is the advantage. So what is the meaning of that is finite element. When you say finite element method, then it introduces the concept of element. You say this is element number 1, so this is element number 1, equal it element number 2. Yeah. Then accordingly, everything remains the same. You are using the Galerkin method only. Only difference is you are suggesting ux, which has finite elements, which has a number of elements, which has a number of polynomials. So number of element means your number of polynomials, number of piecewise polynomials that you are facing. Okay, so that really means actually number of elements is actually equal to number of piecewise polynomial. Right? Okay. So here if you say that two elements, it really means it has two polynomials, two piecewise polynomials. So one polynomial goes to here, another is here to here. Within one element you have only one line, right? And here also but both the lines are different. Yeah, so slope is different. For example, this slope is more, here slope is less, like that. That's the difference. Okay, so this is what it tells you, number of elements equal to number of piecewise polynomials. Okay, so that really means your ux, you will say will be equal to alpha. If it is a line, then you will say it will be like this one. Either you will call it alpha 1, let's say this will be alpha 0 plus alpha 1x for x equal to, let us say you have x equal to 0 here, x equal to 0 here, and here it can be x equal to L over 2, here it can be x equal to L, right. So how will we will formulate accordingly? We will say for x greater than 0, yeah, and less than L, this can L over 2, right. So we have this formulation, yeah, from alpha u x equal to alpha naught plus alpha 1 x for 0 for x greater than 0 and less than L over 2. Similarly, we can say that u x equal to b naught plus, yeah, b naught plus, and then we can have beta 1 x, yeah. So this could be for 0 to sorry, not 0, but it will be from L over 2 x greater than L. You can write like that. Or if it is confusing, you don't know, like we can also write in terms of element wise, you know. So you can have this is alpha u alpha 1 plus beta 1 x, this is alpha 2 plus beta 2 x, or something like that also you can write. So let it be like this one for the time being. We can have different notation if you want to change that way. So what does it give? This is we are going to find out. This is just for example. So you know that at L x equal to L over 2 both should match. So you know that at if you put L over 2 here and L over 2 here, both should be equal, you know. So that constant we have to apply. But this is exactly what it is, from here to here, from here to here, yeah. So this is how we can write, and accordingly we can solve. Actually you can exactly solve this way, okay. Now accordingly your W will also change accordingly, yeah. So let's see the next one. Okay, so far what we got the expression for alpha, this u x and ux, right. So that really means we can solve using this one, and this will be more accurate now. How? Okay, so we start with the weak formulation, right. So we will use weak formulation. Okay, of the same problem, and you know that this will be 0 to L dw over dx Ea, then du over dx, right, and then this will be equal to you have from here to here 0 to L, and then you have b, right, b, then du dx, b w dx, right. Okay, so this is what your weak formulation is. So then we can what we do? We can have du and dw, right. Now w also you can find out. W also we can have the same expression. So we have alpha, the way you have alpha naught, beta naught. Similarly we will have gamma. Similarly we can have gamma, right. So we can have gamma 1 gamma naught plus gamma 1x, which can 4. We can have the same expression. So 0 L over 2 and x equal to lambda 0 plus lambda 1 x, that could be 4 0 sorry L over 2 x L. Okay, and then we know that u has to satisfy some equation, and you know that u in the equation that we have been solving, u at 0 has to be equal to 0, and also we have Ea du over dx at x equal to L is also equal to 0. Okay. Then same thing and also we know that W0 has to be equal to 0 because u is specified as x equal to 0, and hence W will be 0. W at that point will be 0. Hence we know that automatically you will tell that this term has to be equal to 0, and similarly this term has to be equal to 0. Yeah. Okay. Now so that both of them match, so both the points these and these have to match at exactly at x equal to L, right. So that too you have to take care of. That means we can specifically write that u at L over 2 should match, right, should match, right. So that that really means you have some one equation you will get from here, that alpha 1 times L plus equal to beta naught plus b1 L over 2, right, alpha naught. So what equation we will get? We will get alpha 1 times L over 2 equal to beta naught plus beta 1 L over 2. So this is a constant, right. So this is why you are doing this, a continuity, right, say continuity. This continuity is important. Why important? Because you see that if you have like this and this, then this will be C0 continuous, right, C0 continuous or smooth, right. And we need that because we should have du over dx, because this is what we are going to integrate. So we have inside integration we have du over dx term. So if this is not finite du over dx, then we will have problems. So we need to have equal to finite or something which can be calculated. Hence continuity, this ux has to be C naught continuous, right. So okay, so C naught continuous only when this condition has to be applied, then continuity you can say C naught continuity, and because of that has to be there. Similarly for W also you get the same thing. For W also you will have we have gamma 1, right. So we have gamma 1 L over 2 equal to lambda naught plus lambda 1 times L over 2, right. Okay, and then if that is the case, then once you have that, then we are going to have those things here, like inside this equation, both of them, yeah. And then we have to find out values. Which value we have to find out? Actually we have to find out the values of alpha 1, beta 1 and beta naught and beta 1. So there are three unknown things we have to find out. Okay, but there is some one equation which is coming from here. So there are three unknowns among alpha 1, beta naught, beta 1. Two have to be found out. Basically three things we have to, and one thing is already given here. That means there are two equations we need in order to find out. That really means that in a way that only two things are unknown basically, and we have to find out, right. Similarly in this case also it is the same thing, yeah. So anyway we don't have to actually find out this one, because this is at the same time we also write this arbitrary, right. Why? Since W x is arbitrary, yeah, gamma 1, lambda naught and lambda 1 are also arbitrary. Okay. Okay, so if you have to actually find out the solution, what will you do? You will find out du over dx. Okay, so du over dx will be alpha 1 for x, right, for x greater than 0, and du over dx will be equal to beta 1 for 0, sorry, not 0, L over 2 xl. Similarly, dw over dx will be gamma 1 for 0 x L over 2, and dw over dx will be equal to lambda 1 for x L over 2 L, right. Hence, we can write the inside the equation 0 to L dw over dx. So you can write gamma 1. Okay, again we have to write, see here. Now piecewise, so our integration will also be piecewise. So instead of writing this, basically du over dx Ea, dw will be there here. Okay, du over dx will be equal to 0 to L over 2 dw over dx Ea du over dx plus L over 2 to L dw over dx Ea du over dx, right. Okay, so that means we have divided the domain from 0 to L into two parts. First will be 0 to L over 2, second will be L over 2 to L, and we will have in the both of them we will have different w and different u, because this is piecewise polynomial, right. So that means equal to, we can write equal to 0 to L dw over dx for L over 2, we will have gamma 1, right. So we have gamma 1 Ea, then we have alpha 1, right, and dx, right. Okay, plus we have L over 2 is L, and then you have lambda 1 Ea beta 1 dx, right, and hence will be equal to lambda 1 Ea alpha 1 and then L over 2 plus lambda 1 Ea beta 1 and then L over 2 again. Yeah. Okay. So this is what we get. We can also write this as like this, lambda 1 and gamma 1, right, and then we will have something like this. So Ea, we will have Ea L L over 2 alpha 1 and Ea L over 2 beta 1, something like this one we will have. Yeah. Okay. Okay, so this is what we got. The next thing is we can find out this this also. Yeah. So bw dx also we can have that. Okay, so now 0 to L bw dx equal to 0 to L. B is constant for us for that example, and W will have we can have L over 2 W dx plus B L over 2 to L W dx. Okay. Similarly, we can have equal to B, and then 0 to L over 2. Now B is W 4 0 to L over 2 will be equal to alpha gamma, right, gamma 1 x dx, okay, plus you have B again 0 to L over 2, and then you will have lambda naught plus lambda 1 x dx. Yeah, okay, will be B, and then you will have gamma 1 and x square over 2, right. So you have L over 2 square over 2, that's what we will get, plus again B here, and then you get lambda naught, and then you get L over 2, sorry, here this is wrong, so you should have L over 2 to L here, so I will correct it. So okay, so instead of that you should have L over 2 to L only. Okay, so in this case you have lambda naught L over 2 and plus lambda 1 over 2, and then we will have L square minus L over 2 square, like that. Okay, so what we see here is there is a lambda naught term also, right. So you can have from the constraint here that tells you have to be satisfied, and which one, how do you this term has to be satisfied here, right, so this one. Yeah, so that means lambda naught we can write in terms of gamma 1 and lambda 1, right. So this tells us that lambda naught will be equal to gamma 1 L over 2 minus lambda 1 L over 2. Similarly, the okay, so we have the here only. Similarly, this will tell us that beta naught will be equal to alpha 1 L over 2 minus beta 1 L over 2. Okay, so this we can put it in the main equation, and what do we get here? Okay, so will be equal to B, and we have gamma 1 from here we get L square over 8, so L square over 8 plus B L over 2, and then we have lambda naught, so we can write in terms of lambda naught is nothing but let's see here. Okay, so lambda naught is equal to gamma L over 2 minus lambda 1 gamma 1 L over 2 lambda 1 L over 2, right. So gamma 1, okay, so right, gamma 1 L over 2 minus lambda 1 L over 2, we can write that. Okay, so this is done. Okay, so this term we are done with this term now. Okay, so this term is all taken care of. Now we have B times this term, right. So we have B times lambda 1 divided by 2, and then we will have L square minus L square over 4, so 3 L square over 4. Yeah, so 3 3L square over 4, right. Okay. So, finally, what you see we have in terms of gamma 1 and lambda 1 only. So, our equation earlier, the way we wrote here, what did we write? We write like lambda 1, here we wrote lambda 1 and the gamma 1 and lambda 1. So, similarly we can write here in terms of gamma 1 and lambda 1. So, will be equal to, first we write gamma 1, so gamma 1, then lambda 1, and then we can write, so I will write, I will take transpose of that. So, what do we get? So, what is multiplied by gamma 1? So, we have gamma 1 here, then all lambda only we get here. Okay, I think sorry, here since that we have lambda, so lambda will be here, this should be the gamma 1. So, okay, so correction. So, let us write this will be gamma. Okay, this is the gamma. Okay. Okay. So, we have gamma here, a gamma here. So, if we match the coefficient, we will have b L square over 8 times gamma. So, we have b L square over 8 plus b L square over 4 gamma. So, this is gamma 1, sorry. So, we write have gamma 1. Yeah. Okay. So, b L square over 8, b L square over 4, b L square over 4. So, we have that. Then next is lambda. So, the lambda term. So, we have from here we have b over 2 and then 4 times 2 8, 3 over 8. Okay, so 3 b L square over 8. So, 3 b L square over 8. Okay, so 3 b L square over 8 minus, okay, so we have minus will be this b L over 2 L over 2, so b L square over 4 minus b L square over 4. Yeah. So, this is what we get. Okay. So, finally, our equation, if you compare that this not that, if you see our, yeah, this is the weak formulation, this is equal to this one, hence we can write the same way. So, this one whatever we get we will equate that to this one. Yeah. So, we will get the values. Okay. So, the left hand side what we got was this is the left hand side, right. So, let us write it, I will say this left hand side, right. Okay. The left hand side is this one and right hand side will come from here, right. So, this is right hand side, right. So, let us write equal to right hand side. Yeah. So, basically left hand side equal to right hand side, and hence we will have two terms here. So, we will have gamma, we have gamma 1, lambda 1, and then we have this some equation there. So, let us find out which all things are there. So, left hand side is this, and we have EAL over 2 alpha 1 beta 1, that is what it is, right. So, EA L over 2 EAL over 2. So EAL over 2 alpha 1 EAL over 2 beta 1 will be equal to, we have similar kind of things here as well. We have gamma 1 lambda 1. So this is right hand side, and from right hand side the lambda 1 sorry gamma 1 lambda 1 multiplied by this one. So we have BL square, so 1 over 8 and 1 over 4. So we have 3 over 8. So 3 over 8 BL square. 3 over 8 BL square. So 3 over 8 BL square. Yeah, okay, and this term will be, so 2 here, 2 here, so BL square over 8. BL square over 8. Okay. Okay, so see here, we got this equation now. Yeah, we got the equation now here, and since we can say now, since gamma 1 and lambda 1 are arbitrary, okay, if this is equal to, if these and these are arbitrary, hence only way this has to be equal to this will be, this whole thing will be equal to this thing, right. So this tells you that EA L over 2 alpha 1 beta 1 will be equal to B L square over 8, and we have 3 and 1. Yeah, and hence you will get alpha 1 and beta 1. Alpha 1 beta 1 will be equal to, so we have L here, so you have L square here, so we have L from there, and then so this is EA, so we get L over EA, and then 2 and 4 here, so we get simply L over 4 EA, right. Okay, and there will be B as well. Okay, so what do we get? B L, okay, over 4 because of this, and EA. Okay, okay, we got that, and then we will have 3 and 1, right. Okay, or this is equal to basically 3 B L over 4 EA, and this will be BL over 4 EA. Yeah, so these the answers you got. You got alpha 1 and beta 1. Now we also need to find out beta naught. Okay, so beta naught is not known, right. So we have to use the equation. Which equation? So if you see we had one here. So beta naught equal to alpha L over 2 means equal to alpha 1 minus beta 1 times L over 2. It is simply is alpha 1 minus beta 1 times L over 2 is beta naught. Okay, so accordingly we can find out beta naught, right. So beta naught equal to alpha 1 minus beta 1 multiplied by L over 2, and which is equal to, we know from here that alpha 1 minus beta 1 will be equal to nothing but this minus this, So 3 minus 1 will be 2, 2 over 4 half. So BL over 2EA, BL over 2E. So you will get BL over 2EA multiplied by L over 2, and you get BL square over 4EA. Okay, so this is what the V naught is, and hence our equation, now you know what is the solution. So your solution is obtained becomes U x equal to will be alpha 1 times x, because alpha naught is 0. So alpha 1 will be nothing but 3BL over 4EA, 3BL over 4EA x. This is for x greater than 0, less than L over 2, and similarly Ux will be equal to, you have beta naught first. Okay, so you have beta naught, so you write B L square over 4EA. Okay, fine, and then you have plus, so BL square, so BL square over 4EA. Okay, and then second term is this is B naught plus beta 1 beta naught plus beta 1 x. So what is beta 1? So beta 1 we get from here. Beta 1 is nothing, BL over 4EA. So BL over 4EA. So we get BL over 4EA times x, and this is for x greater than L over 2 and less than L. So this is the solution we got, so piecewise polynomial. Yeah, so this is a long way to go basically, and what you saw is we had to also have the constraint, in terms of we had to maintain the continuity, right? So we had this constraint we had to apply, this constraint we have to apply. So all those things, hassles are there, but we have actually solved it. So you can see even like whether U is the same as LO over, you can check at like U 0, right? So U0 will be equal to 0 only, right? So since this is applicable, so will be equal to 0. So you have applied already. We can also see the U at L, right? U at L over 2. U at L over 2, if you apply, put a L over 2 here, so then becomes 3BL square. So from the first equation you get 3BL square over 8 EA, right? So we get 3BL square over 8 EA. From here what do you get? Put L over 2 here. So L over 2 here, so we get 1 over 8 here, and this becomes 2 over 8 here. So 2 plus 1 3, so you get 3. Here also you get the same thing. Yeah, so from both UX, right? So hence it maintains the continuity, so continuous. You can find the U at L, and U at L will be equal to, now this will be applicable, so you put L here and you get BL square over 4EA, and this is also BL square over 4EA, means it will be, answer will be BL square over 2EA. So UL will be BL square over 2EA. Now we can compare it with the actual solution. Yeah, so the solution, I think in lecture 11 or so we worked on the solution, and we found out the correct solution or the solution. Okay, or you can say this is the analytical solution, or okay, analytical solution or the correct solution or accurate solution is Ux equal to minus B over 2EA x square plus B L x over EA. Yeah. We have used B naught, E naught, A naught, B naught, E naught, A naught. So, but what is mean is actually the same thing. Okay, so we have B, E, A given, and we have this B here like this one. Same, we are assuming B, E, A all constant. So this is constant, E is constant, A is constant. So we wrote like this. So this is the actual solution, right? So this is the correct solution. If you plot this one, then let's write that the analytical solution you write is UA, this analytical solution. Okay, so we have you can have x here and then ux. The actual solution will go something like this, right? Yeah, so like this one. So at the end this will be slope will be 0. So this is how this is at L. Yeah, okay. So the value you can have actual solution, this value you can put L here, and we will say a BL square over EA, BL square over 2. So hence BL square over 2EA. So value will be BL square over 2EA. At in the middle where you have L over 2, you can put L over 2 here, L over 2 here. So you get BL square over 2EA. Here you will get BL square over 8EA, this minus. Okay, so here you have 2, 1 over 2 BL square, here BL square over 8. Yeah, so 2 times 2, 2 times 4, sorry, here you will have BL and L over 2. So 1 over 2, so you have 4 over 4, so you get 4 over 8. So you have here 4 by 8 BL square, you have 1 over 8. So 4 minus 1 is 3. So the value here will be 3 BL square over 8 E. Yeah. Now see the piecewise polynomial. If you have taken 2 elements, so then their solutions are like this. Actually, we know that UL over 2 is 3 BL square by 8 here. Exactly, it matches the exact solution, right? Analytical solution or called exact solution. You write this is exact solution. Yeah. So what we got, and but this is linear, so it goes like this one. So the first goes line like this one, the second also goes like this. Yeah, so this follows so accurately. It goes from here to here, and then it goes from here to here, and actually U is matching at this point, and this is what this method. Yeah, this one. This is this one. Okay, so we can write this is 2. Okay, maybe not. Okay, we say this is 2 piecewise polynomial. That is this one and this one. Yeah. Okay. If you compare with the earlier solution, you remember, so we had the earlier solution, when we assumed only one element throughout, yeah, in that case we got something like this only, right. So this yellow is only one element, right. So this one is linear, means if you assumed ux equal to simply a not a, let us say a plus bx. If you had a single element basically, yeah. So if you have just a plus bx, if you assumed u for the whole element, then it will be just a line like this one. If you take two lines, means piecewise linear solution, then it will go from here to here, and this is the accurate one. Yeah. So you also see the difference basically. Yeah. So hence the piecewise polynomial is so good, you know. So even you can increase the number of polynomial, meaning that number of elements. So this is just one element. You are taking the trial function as a line only, but only one element. This is a trial function with line only, but two elements. Similarly, you can have 3. So this will be even closer. 4, even more closer. 5, or maybe 6, 7. You will see there is no difference basically. You will see it's so closely it will follow the exact solution that you will not be able to see any difference. Yeah? So this is what the philosophy behind using piecewise polynomial as a trial function, or this is the philosophy behind introducing the elements basically. So this is how the concept of element comes into picture. Okay, so this is the real reason.